The point of the field of study of heat transfer is supposed to be to understand how temperatures change not just in space, but also in time. Remember that the key motivation that drove us to create the field of heat transfer in the first place was this physical observation that when I took two objects that have different temperatures and I put them together, I observe, oh, their temperatures eventually become the same. And we've worked on a bunch of examples where we've been able to use, certain mathematical tools that allow us to understand how temperatures change in space, but we never really dealt with an example where we've had to understand how temperature changes over time. And so if we are trying to develop a coherent field of study that addresses that particular experiment of the fact that temperatures between temperatures of different objects eventually equilibrate to the same thing, if we want to actually create a field of study that addresses that, we have to create an equation that quantitatively describes how that occurs. And so in order to do that, we have to address something that we've been trying to avoid for a very long period of time so far, which is what thermal energy is as a function of temperature. So we never actually wrote down what thermal energy was, what the thermal energy of a system is as a function of whatever its temperature is. And the reason that we never did this, the reason we never had to, was because in all of the systems that we've been studying, the thermal energy, the rate of change of the thermal energy over time of that system has been zero. We've always dealt with systems where either because of thermal energy generation or some implied source of thermal energy, the thermal energy of every system or every region in space or whatever has been constant. The rate of change has been zero. But now, if we want to study how temperatures change over time, we have to study how thermal energy changes over time. And so as a result, we have to actually kind of take a look at how we can create an equation for this. Now, this is the part of the lecture where you can certainly expect a professor to go into a lot of details about, well, what is temperature? What is thermal energy? How do these things relate using principles from statistical mechanics and kinetic theory? But we're not in fields of study where we do that, right? The methodology that we've created for this new field of study, at least to us, is to basically come up with the simplest possible equation that we can, and then load all of the physics into a coefficient that gets attached to that expression. So how are we going to do that in this particular case? Simple. Well, the first thing that we should do is to not necessarily worry about the actual expression for the thermal energy as a function of temperature. Okay, we're not really going to necessarily care about this for now. What we are going to try to do is to try to write down an expression for what changes in the thermal energy of a system are as a function of changes to its temperature. Okay, so what we actually care about is understanding how the thermal energy of a system changes whenever we change its temperature. That's the goal here. So what can we say about this? Well, we can say similar things that we said to the, I guess, ideological modeling technique that we had for heat fluxes in the previous two equations that we developed, which is to say that we can assume that, assuming we don't fiddle around with the system in a weird way, whenever changes in temperature in our system are zero, that the change of the thermal energy of the system is also zero. Okay, we can just kind of assume that. And we can also go in and assume that we are operating in some regime where changes in temperature are small. Again, this is super ad hoc. We don't actually know what smallness is when it comes to absolute values of temperature difference. But nevertheless, we can imagine that there's some regime where we can assume that these delta T's are zero and hope that that regime includes all of the stuff that we observe on Earth. And if we make this assumption, then just like we did for the previous two equations that we've developed, we can just go in and say, well, this is well approximated by a linear relationship where changes in the thermal energy are just proportional to changes in the temperature multiplied by some coefficient that contains all of the actual complicated physics of this problem. Okay? And this coefficient is commonly referred to as the heat capacity. Okay? And so there's no physics here, right? We've done the exact same thing where we're just trying to come up with the simplest possible equation we can. And the simplest thing we could come up with, just like in the previous two cases, was a linear relationship between the thermal energy and the temperature multiplied by this heat capacity. Now, this heat capacity, just like the heat transfer coefficient and the thermal conductivity that we developed in these other equations, just like those other two things, the heat capacity is experimentally derived. And it can depend on all kinds of things, right? It can depend on the mass of the object. It can depend on the Young's modulus of the object. It can depend on its viscosity. It can depend on all kinds of things. It can depend on the temperature. It can depend on the pressure, right? So just like the heat transfer coefficient and the thermal conductivity before it, this is also just this arbitrary experimentally derived coefficient. Now, this, however, is not actually how you usually see physicists or engineers refer to this equation, right? Because this depends on too many things. In particular, the fact that it depends on mass is not great, because it means that, you know, this isn't really a material property, or at least you can't try to justify to yourself that this is a material property if it depends on mass. And so what people like to do is to say, well, okay, let's split that constant up even more, right? Let's split that coefficient up into more pieces and then create an expression that looks like this. And now what we're trying to say is, okay, well, now the thermal energy is still proportional to changes in temperature, right? But now we're also going to assume that it's proportional to mass and to this other funny little quantity that I've just defined, such that when you multiply the mass and this thing together, you wind up getting the heat capacity, all right? And so this is the mass of the object, whatever it is that we're studying. And this thing right here is usually referred to as the specific heat capacity. And so the whole point is supposed to be that we are splitting up the heat capacity into this and this, just so that we can remove a dependence on mass, right? So that we can try to at least tell ourselves, even though it may not be true, that this specific heat capacity is a material property, okay? And if you take a look at what the units of these quantities are, we can figure it out relatively quickly by just checking how they relate to other things, right? So what are the units of the heat capacity? The units of heat capacity, it's supposed to represent a ratio of thermal energy to temperature, right? Of energy to temperature. So in the International System of Units, this will have units of either joules per degree Celsius or joules per Kelvin. All right? So that's what the units of heat capacity are. And then we can use these units to try to figure out what the units of the specific heat capacity are going to be, right? So the units of mass and in the international system are just kilograms. And so by extension, the units of the specific heat capacity are such that when we multiply those by kilogram, we get joule per degree Celsius or joule per Kelvin. And so the specific heat capacity has units of joules per kilogram degree Celsius or joule per kilogram Kelvin. Okay? And so if you think about it, right, we have hypothetically removed the mass, or we at least would like to think that we've removed the mass as something that the specific heat capacity can depend on, but all of the physics has now been front-loaded onto the specific heat capacity, right? So whenever we see this equation, we have a pretty good understanding of what the mass of an object is. We have a pretty good understanding of what the delta T is. We can derive what the mass of an object is by its volume and its density or its molecular mass or whatever. But we don't really have a good argument for what the specific heat capacity is as a function of, you know, fundamental physical things that are properties of the system or stuff like that. So ultimately speaking, the fudge factor, right, the experimentally derived thing that we've, you know, offloaded all the physics onto is now the specific heat capacity, all right? And so keep that in mind whenever you see expressions for the thermal energy. This CP, this specific heat capacity, plays the same exact conceptual role that the heat transfer coefficient and the thermal conductivity do in the equations where we use them. All right. And so to finish this off, the thing that happens very often is that people will say things like, well, it actually doesn't matter what the energy of a system is. The only thing that matters are what the changes of the energy of that system are. That physics isn't determined by absolute values of energy, but only by changes in that energy. And so if we assume that this is true, then it actually doesn't matter how we define the thermal energy. All that we have to do is to make sure that changes in the thermal energy are accounted for using the equation that we just developed. And in that scenario, right, in a scenario where this is true, or at least that we can approximate this as being true, very often people will just say, well, again, who cares about the absolute values of energy? So let's just make our lives easier and get rid of the deltas. And then just arbitrarily say that the thermal energy of a system is just equal to the specific heat capacity times the mass times the temperature of that object. All right. And so once again, no physics here, right? This is just super, super rickety. And all of the physics associated with what's going on, like what actually is the physical process that relates to these things, is contained inside of the coefficient that we call the specific heat capacity. All right. And so this was a relatively quick lecture where we had to derive this expression. And now we're going to go into a more mathematically complex lecture where we actually have to take this expression and plug it into some of the other equations that we've used so far to be able to derive something that tells us how temperature changes over time, which we will do in the next lecture.